All right, so we took a test. I hope you did well. I will be grading both of those tests. I completely apologize for that slipping off my radar. To grade that test this last weekend, I will get those graded as soon as possible. All right, so look at this. Oh, I didn't have it show up in a fun way. But anyways, look at how far we've made it down our metaphorical river. In fact, we've made it to our metaphorical Hance Rapid. In fact, this might be an appropriate metaphor because Hance Rapid, if you are aware, is one of the biggest, roughest rapids in the Grand Canyon. Maybe not the biggest, but it's one of the big ones. And so that's going to be about where we are today. You can see, I mean, it might not look much, especially from up above. See, that doesn't look so bad. But, you know, in the metaphor of statistics, maybe you're getting to the point where the waters are getting kind of choppy. And hey, here's a video. It might be a bit choppy. I mean, no pun intended. But when streaming, it doesn't necessarily come through smoothly. I can't remember if this one has slow motion in it. But some of the other videos I showed do have slow motion. All right. Well, this is where it gets to the big stuff. I know it's very choppy. You're not seeing the video clearly, but you can hopefully see some of the scenery around it. So there we go. And we're gonna, that's basically it. So if you want to see a video of that, you can look it up. Just Hance Rapid, you'll find lots of videos. I know that's not why you showed up to class, so you can learn more about the Grand Canyon. But hey, that's where we are metaphorically, and this is where we are in actuality. We're at the intro to probability. Okay, so this is the part, and you know, some stats teachers save this until the very end. They go through everything else and then they come back to probability. It's actually worth it to talk about this now because there are some concepts that do come into play, specifically about independence and of course, if you read the chapter at all, chapter 14, you already read about this to some degree. But there are some concepts that if we talk about it now, it's going to help out as we build on it later, though I could have done this in a different order. Anyways, probability. So maybe the first thing to mention is that our unit 5, which probability unit 5, there are reference posters, and I have reference posters for every unit except for the last one, but they do a really good job of summarizing the concepts, including some of these we're starting to look at. So these are some of those: law of large numbers, complement rule, addition rule, multiplication rule. Some of the other concepts called the general addition rule and general multiplication rule are also in the reference posters. So this is going to be good for the entire unit, but we're not introducing those today. So, you know, come back to those later. So there are some terms in probability that are important to know. Now, it's more important to know these just from a recognition perspective. It is unlikely you're going to get any AP style question where it's essential that you know what empirical probability is. but they might throw out the term. Okay, so empirical probability, this is the probability that comes from observation. So if we look, the FHS girls soccer team seems to win 90% of all their games. Therefore, historically, and we can assume moving forward, and their empirical probability of winning is 90% any given game. Of course, we know that's assuming a bunch of stuff to be equal. Theoretical probability is a probability that comes from a model and calculations. So we can figure out theoretical probability pretty easily. So if you have a random deck of cards, if you want to draw one specific card like the ace of spades, you have 1 in 52 chance of getting that. We know that. We don't have to come up with a complex theorem to prove that. It's just an intuitive idea, but it still comes from calculations, not from us trying to pull the ace of spades 1,000 times and coming up with the realization, oh, it's 1 in 52. We figured that out just based on the math. Personal probability, this is kind of an obscure topic or term, but it's one's own subjective assessment of the likelihood. So you might personally be 100% sure that you're going to ace this probability exam. Now, it's a personal probability. It's not like a mathematical one. And I hope everyone's 100% sure you're going to ace this test. Sample space is the collection of all possible values. And this is a term that might come up more frequently than the other three. So your sample space, similar to your sampling frame, remember your sampling frame is a list of everyone who could possibly be included in a sample. A sample space is the list of all the possible outcomes of a particular event. So the sample space for a coin flip is heads or tails. I mean, maybe the nitpicker out there could say, oh, it can land on its side, but yeah, it doesn't. Heads or tails. The sample space for suits in the deck of cards would be hearts, diamonds, spades, clubs. All right, and notice that it's these curly brackets. Again, that's just kind of formal notation for it, but it's probably not going to be a big deal as far as memorizing that notation. Okay, this notation you will see quite a bit. In fact, it's on your AP reference sheet already. So you want to make sure that you're familiar with this. The first one is just the probability of an event A happening. Whatever that event A is, what's the probability of it? You just write it like that. Here's the probability of event A and event B happening. And there's the probability of event A or event B happening. So or. And I'll come back to those two in a second. The probability of event A not happening, this is the complement rule. And so you can see we just use this superscript C right here, almost as an exponent, but that just means that it's a complement. So if, let's just throw in some number here. If the probability of A happening is 0.2, then that means, therefore, the probability of a complement is going to be 1 minus the probability of A. And so it's going to be 1 minus 0.2, and that's 0.8. You probably did that in your head, but just to show kind of the full process for getting to our final answer, that 8, there it is. So this, it might seem ridiculous, like, why do we need a probability of A complement? Why don't we just use probability of B? Yeah, well, just to give you kind of an answer at the beginning, and we'll see this a lot more, if you have a lot of events, if it's just A and B, 2 events, if there's just 2, whoa, what did I just write? What is going on in my life? Sorry, I just created a new letter. Okay, if there's just 2 events, then we're saying the probability that event A happens or that event B happens, well, or the probability that A doesn't happen. Anyways, these two, go together. But of course, in a lot of cases, there could be lots of different events. So that's where this complement rule comes into play. Where if you're dealing with like 4 different events that could happen, the probability of A not happening is going to be all of these. And it's a lot easier to say, what's the probability that A doesn't happen, rather than saying, what's the probability that A or that B or C or D happens? Okay, hopefully I didn't confuse anyone with that. So one way that might help you remember this notation up here, as far as these two go, for the and, since you're dealing with and A, you can think of this symbol right here as like an A. That might help you remember that. The other thing that it's important to know is that an or is sometimes also called a union. So you can think union right here. And the other name for this is an intersect or intersection. Okay. And to make sense of that, oh, I never did end this poll. I'm sorry. All right. So to make sense of that, and there's actually some diagrams in those reference posters that kind of show this. If you have two events that happen, and you think of these as a Venn diagram, the reason they're called an intersect and a union is that there are lots of different outcomes, perhaps, that is the probability of A happening. Okay, and this won't make, maybe some of the stuff I'm saying won't make complete sense, but an intersection is like this narrow slice right here in the middle. And that's the area where event A and event B both happen. So that's why we call it an intersection. And then if it's A and B right here, and we're saying it doesn't matter, it's either one of these, then it represents this space right here, which is the union of both of those. And what we mean by this when we say, like this has area to it, like this A represents a certain area. Let's say this represents 0.2 probability, and this represents a 0.2 probability, since I drew them about the same size. And they both seem to be about 1/5 of the total area, which is 1.0. So we can draw things proportional to their likelihood. And that's just kind of a visual way of making some probability happen. Okay. Like always, if that confused you more than helped you, I'll try and fix that if you want to stick around and ask some questions. Probability properties. I've already been using some of these properties, and some of these you're familiar with already. Probability has to be between 0 and 1. So probability of 0 means that it is impossible for something to happen. So a probability of 0 is normally pretty hard to get. Now, if it's a complete, I don't want to say paradox. If they're just complete, I'm trying to find the right word for it, the complete contrast. So an event like a coin, do I have an example? No, I don't. So like a coin landing on heads and landing on tails at the same time is 0. But a coin landing on heads or on tails is going to be 100% likely. All right. So they can be expressed. It doesn't matter if you want to put it in terms of decimals, fractions, or percents. We'll use decimals and percents pretty evenly. Fractions will show up every once in a while. There are no units for probability, and the combined probabilities of all outcomes in the sample space must add up to 1. This is going to be an important thing when we get into conditional probability. So while drawing any particular card in the standard 52 card deck has a probability of 1 in 52, the probability of all the outcomes added up is going to be 52 out of 52. Okay. And this is a concept, we're going to introduce it today. I'll try and hit the highlights of how we're going to use this and how you can kind of, let's just get to it. Okay, 2 events are mutually exclusive if they cannot both occur. So I already gave some examples of this. So while 2 dice are independent, since they don't affect each other, and we'll talk about independence in a second, the event of rolling a 6 is not mutually exclusive since both could land on the same number. A house that has a garage is not mutually exclusive with that house having air conditioning. A house can have both a garage, and air conditioning. And contrast that with college choices. So some of you might be, at this point, hopefully a lot of you already decided on where you're going, but you could still be making choices. But if you're applying to a lot of different colleges and you haven't picked yet, those are mutually exclusive. You can't go to all the colleges that you're applying to. You have to pick one of them. So it's mutually exclusive. They are also called disjoint. And maybe a question to determine if something is mutually exclusive: is it possible for the second event to occur if the first event occurs? If not, they're disjoint or mutually exclusive. And we would say it this way: if you were going to draw a Venn diagram of this, A and B, they would not intersect at all. They would be disjoint, and that's where the word comes from. Okay, we can think about this mathematically, and that the probability of both events happening must be 0, because they can't both happen at the same time. So this formula is going to be an important one. Okay, so there we go. The probability of attending ASU and attending U of A is 0. I mean, I guess we should say at the same time. The probability of a coin landing on heads and that coin landing on tails is 0. They are mutually exclusive. And the probability of acing your next stats test and failing that same test is 0. Must be one or the other. Of course, we know where you guys are going to fall. You're going to ace it. All right, so this formula is going to be an important one. And we will come back to this. Will we come back to it? Well, I would like to come back to this. Hopefully I have the slides. I'm going to note to myself. Okay. Mutually exclusive. Here's another way of looking at it mathematically. The probability of both events happening, the probability of both event A happening or event B happening must be the same as the probability of the each event individually happening. So this formula is going to be an important one. This formula is only true if the two events are mutually exclusive. So the probability of landing, let me see if I have an example here. All right, if the equation doesn't work for our data, then we can infer that the events are not mutually exclusive. So before we jump into a problem with that, if we just do the most basic thing, the probability here, mutually exclusive, is that we get a hearts and then that we get a spade. So you can't get a heart and a spades with one draw from the deck. So the probability of getting a heart is 0.25. The probability of getting a spade is 0.25. Now the probability of getting a heart or a spade, that represents half the deck. That's going to be 0.5. Now because these two add up, that will show up in a second. Okay, because these two add up to 0.5, we can see that they are mutually exclusive. Okay, that was weird. It wasn't showing up on my screen. All right, so here's an example. The probability of someone taking calculus at flag high is 0.04. So, and I'm making these numbers up. So let's just say the probability, this is the probability of calculus. This is 0.04. Probability of someone taking statistics is 0.05. So this will be 0.05. So this will be stats. And that's going to be calc. The probability of someone taking stats or calculus is 0.08. Now, does this equation work? This basic math, I can see 0.08 equals 0.09 when I add up on the right side. No, they do not add up. And I apologize if my internet's going a little slow right now. All right, so because they don't add up, we can determine that they are not mutually exclusive. And what that means is that you can take, and some people do, take calculus and stats at the same time. All right. All right. Independence. So okay, let's just move into independence. Independence in probability means that the outcome of one event has no effect on the outcome of another. These two almost seem like we're talking about the same thing, but it's hopefully by the end we can clarify what the difference between these is for everyone. So when you roll two die, one die does not determine what happens on the other. They are completely independent. Picking which shirt you wear tomorrow night will not be independent if you want it to match the rest of your outfit. So if you put on certain pants and you decide you want a shirt to match it, then you have changed the probability of which shirt you're going to pick out from your closet. So the question asked for this one is, does the first event happening change the probability of the second event happening? If it does not change the probability, then the events are independent. Okay, so we'll look at this is with the multiplication rule. The probability that event A times the probability of event B is the probability of events A and B happening. But this is only true if the events are independent. Okay, the upshot of this is that if the probability of A and B equals the probability of A times the probability of B, we can infer that the events are independent. All right, again, so if we looked at, this one won't be as straightforward. Let me do a very simple scenario. We're going to flip two coins, and we have four outcomes. I could get heads 2 times. I get heads then tails. I could get tails then heads, or I could get tails 2 times. So the probability of getting a head is going to be 0.5. So this will be heads. And this will be tails. That's 0.5.
Wait, quick question.
Yeah.
So since you have the probability of getting a heads 75% because it's in 3 of them?
Okay, well, actually, I'm going to change the setup of this scenario. We're going to find the probability of getting a head and getting a head. All right, so getting a head twice in a row, because this can get more complex if I don't have it set up this way. The probability of getting heads and heads. So the probability of getting heads, that's going to be event B, is 0.5. All right, so if I multiply that together, the probability of getting heads and heads in a row, we can already see right here from this, that's 1 in 4. There's only one outcome of the 4. So it's 0.25 has to equal 0.5 times 0.5. And of course, we can see that is exactly what we get. So turns out that in this case, the probability of getting heads and heads, those two events are mutually exclusive. Or sorry, they're independent. I got to get my terms right. They are not mutually exclusive. They are independent. And they're not mutually exclusive because you can get heads and then heads. There's nothing wrong with that. Okay. So here we go. Here's where a practical problem might come into play. The probability of having problems with your transmission is 1 in 75. The probability of a car having problems with their radiator is 1 in 25. So we got a couple of probabilities. I'm going to say this is event A right here. So this is the probability of A, and this is the probability of B. Now the probability of having car problems with transmission and the radiator is 1 in 100. So this is the probability of A and B. So I'm going to plug this into my formula. Are these independent? I'm just going to do some replacement here, and so I'm going to replace probability of A and B with 1 in 100. And probability of A is 1 in 75. So I'm just going to replace that. And the probability of B is 1 in 25. So when I multiply this out, let's see, I'll just do that real quick. 75 times 25 is 1,075. So 1 in 100 equals 1 over 1,075. So this, we can see, this is not equal. So therefore, these events are not independent. It looks like having problems with your transmission increases the probability of having problems with your radiator and vice versa. Okay, I'm going to pause right here. Are there questions on this so far?
No.
Okay. So I do also, of course, always recommend you read the book because maybe the book explains it in a way that clicks for you. So I did want to come back real quick before we finished up. We talked about mutually exclusive. Let me come back here. There it is. We talked about this. The probability of A and B has to be equal. All right, and we know that well, maybe that isn't appropriate to talk about this right now because we're going to get into the other multiplication rules later. So I had an idea of something to talk about, but I think I'm putting the cart ahead of the horse if I do that. So let's just simplify it there. And here's your homework. I did put a worksheet up in the Canvas page. I don't think it's published yet, so I'm going to make sure I go and publish that so you'll be able to see it after this class is over. But anyways, read anything you haven't read in chapter 14. I think reading combined with being in class, combined with the worksheet and everything is going to help solidify this understanding. Luckily, this stuff does build on itself. So we're going to keep coming back to the idea of independence and mutually exclusive. If it's not making sense right now, we're going to keep seeing it. And I promise you're going to have enough opportunity to really solidify that understanding. But anyways, I'm going to cut it off right there. If you have questions about anything, please stick around. But other than that, you can have a wonderful day.